How can engineers visualize complex turbulent fluid flow? Imagine trying to understand a wild river's swirling currents or the chaotic air around an airplane wing. How do engineers make sense of such unpredictable, swirling motions? That's where visualization techniques come into play. Visualizing turbulent fluid flow is like turning a stormy sea into a map you can read. It helps engineers see the hidden patterns and structures within chaos. Turbulent flow is different from smooth, orderly flow. It involves swirling eddies of all sizes, from tiny whirlpools to large vortex structures. These eddies cause irregular fluctuations that are tricky to predict. To study these, engineers use a mix of experimental methods, computer simulations, and high-tech imaging. One common way to see flow patterns is through flow visualization techniques in experiments. For example, surface flow visualization uses oil films or small tufts attached to surfaces. Oil streaks show how fluid moves along boundaries, revealing flow separation or reattachment points. Tufts are tiny threads that align with the flow, indicating regions where flow detaches or reattaches. These methods are simple but effective for understanding boundary layers and drag forces. Another powerful tool is Particle Image Velocimetry, or PIV. It uses laser sheets to illuminate tiny particles seated in the fluid. High-speed cameras record their movement, and software calculates the velocity at every point in the plane. PIV provides detailed pictures of turbulent structures and how they change over time. It's like capturing a high-speed movie of chaotic flow patterns. Hot wire anemometry is another technique. It involves a thin wire heated electrically. When fluid flows past, it cools the wire, and the cooling rate tells us about the local velocity and turbulence intensity. This method captures rapid fluctuations, giving a detailed picture of turbulence at a point. Optical methods like Schlieren and Shadowgraphy visualize density differences in fluids. These are especially useful for flows involving temperature changes or shock waves. Schlieren imaging bends light to show high-contrast images of turbulent mixing or shock interactions. Shadowgraphy detects light deflections caused by density variations, revealing turbulent regions. High-speed cameras also play a role. They record transient phenomena like vortex shedding or flow instabilities as they happen. Watching these videos helps engineers understand how turbulence evolves and interacts with surfaces. Computational fluid dynamics, or CFD, is a digital way to visualize turbulence. It solves complex equations that describe fluid motion on computers. Engineers generate visualizations like streamlines, which show the path a fluid particle would follow at a specific moment. Path lines trace actual particle trajectories over time. Velocity vectors and vorticity contours highlight rotational regions and flow structures. These images help identify vortices, separation zones, and turbulent mixing areas. Using CFD reduces the need for physical models and allows testing many scenarios quickly. It's especially useful in designing aircraft wings, turbines, or heat exchangers. It helps engineers see how changes in shape or conditions affect turbulent flow. Throughout history, visualizing turbulent flow has been a challenge. Early sketches by Leonardo da Vinci showed swirling eddies, but today's tools provide detailed, quantitative images. Combining experimental data with computer models gives a full picture of how turbulence behaves. Engineers use these visualization methods to improve designs, reduce drag, enhance heat transfer, and predict environmental impacts. By turning chaos into images, they gain the knowledge needed to control and optimize fluid systems. That's how they make the invisible visible and tame the turbulent.